Вы что, говорите, пошли? Я просто нет.
Here you can see it.
Oh, that's the Zoom.
Yeah.
Emil giving it. Okay, not many. Okay, maybe we can start. Are you going to do anything or I just start?
Okay, welcome PCS members and friends to our today's PCS IBS seminar. It is a pleasure to have with us today Professor Emil Yuzbashyan from Rutgers University. And our scientific host today is Sergey, and he will introduce our speaker. Please, Sergey.
Yeah, and thanks. And question, do we YouTube or we don't YouTube?
We do YouTube.
It's already on, because usually you say, now we are on YouTube, and then I know that things are serious. Okay, it's a pleasure to have Professor Emil Yuzbashyan with us today here, who's visiting us for a couple of weeks or actually a month. Emil was visiting us before the pandemics, and he's one of our first visitors. So if you go back to our visitors, Ahnengallery, I don't know how to say that in English, the gallery of the previous people, so to say, you will find Emil among one of the first visitors. He did his Master of Sciences at the Moscow Institute of Physics and Technology in '95, and moved then to Princeton University, where he did finish his PhD in August 2004. And then he had several positions, or in the meantime, he had several positions at various places, like, for instance, the Joint Institute for Nuclear Research in Vienna, and the physics department in Chicago. And then he moved right after his PhD to Rutgers University, where he started as an assistant professor and then worked his way through from associate to full professor since 2017. He has a number of awards. I will not read them all. And I want to say that he has co-authored a lot of influential publications. He is an expert in condensed matter physics, but also a bit, I could also say, in mathematical physics and integral systems. So it's quite a broad spectrum of expertise he brings with him to us. And today he will tell us news about how the electron-phonon interaction metals can be. And before you start, Emil, yes, I just want to mention that he's also going to be one of the speakers at the Dynamics Days Asia Pacific conference next week, and there he will speak about something different. So don't miss the second talk there as well. So let's welcome Emil.
Thank you, Sergey, very much for the introduction, and thank you for having me here. I always enjoy, coming to this center. I think it's a very good place to do work and to collaborate. The conditions here are ideal for that. The main question that I'm going to address today is how strong the electron-phonon interaction in metals can be. So here you have to realize that according to the existing theory of solid-state physics, the electron-phonon interaction in metals can be arbitrarily large. But what I'm going to show today that in fact there is a fundamental limit on the strength of this interaction. So this talk is based on two papers written together with my collaborator Boris Altshuler, who is here with us in the audience. Okay, so electron-phonon interactions are interactions between free electrons and the crystal lattice, or more precisely, interaction between electrons and lattice vibrations. So these interactions are responsible for most of the electronic properties of solid. In particular, they determine the band structure, electrical resistivity, specific heat, charge density wave order, and superconducting order in metals. And about these last three, we will talk in more detail later. So there are two approaches that you can take to the electron-phonon problem. So the most fundamental approach is to start with the so-called standard model of solids. So from the first principles, where you have some Me electrons that interact between themselves with Coulomb interaction, then you have ions that also interact via Coulomb interaction and also interact with electrons. But this model is extremely complicated, and it's basically impossible to get very far from with it. In particular, it's impossible to treat the electron-phonon problem as of today, starting with this model. So an alternative approach is to derive an effective Hamiltonian for electron-phonon interactions. So the problem then becomes more treatable, but we always have to keep in mind that there are questions that remain outside of the domain of applicability of the effective Hamiltonian approach. So let me show you two famous, most frequently used and most famous effective Hamiltonians. So the first one is Holstein Hamiltonian. It builds on the model of solids proposed by Einstein, where you simply model each ion at the lattice side as an independent oscillator. Then you have electrons hopping on this side, on this lattice that can be, let's say, three-dimensional, two-dimensional, or arbitrary dimensional, and also the electron-phonon coupling. So this model is good for optical phonons that have some constant frequency. A model was proposed earlier by Froelich, the Froelich Hamiltonian, which was originally proposed, for acoustic phonons. So here it's very similar to this model, but I just wrote it here in momentum representation. So this is the kinetic energy of the fermions. This is the energy of the phonons, lattice vibrations, and now we allow phonons to have dispersion. So the phonon frequency can depend on the momentum Q. And this is the electron-phonon interaction, whereby an electron can emit or absorb a phonon and change its momentum. So it was the advent of Froelich Hamiltonian in 1950s, and well, I jumped a little bit ahead here. I'll come back to that, event, but let me just first say here that, as we'll see, the main conclusions of this talk are independent of the choice of the effective Hamiltonian. So let us work with a simpler Holstein Hamiltonian, and let me explain the Hamiltonian one more time, because I'm going to use it throughout this talk. So we have fermions hopping on some arbitrary lattice. At each lattice side, we have an ion that is independent oscillator with mass capital M and spring constant K0. And also we have electron-phonon interaction, which is proportional to the oscillator displacement and to the number of electrons on site I. So, as I was saying, it was advent of effective Hamiltonians like this and the penetration of field theory methods into solid-state physics that allowed Arkady Migdal to construct a theory of electron-phonon interactions in metals that to this day is unmatched and remains the most successful theory of this interaction. So here is the abstract from his paper. A method is developed which enables one to obtain the electron energy spectrum and dispersion of the lattice vibrations without assuming that the interaction between electrons and phonons is small. So below a certain critical temperature, metals become superconductors. And 2 years later, Gerasim Eliashberg extended Migdal's theory to the superconducting state. So you might be more familiar with the BCS theory of superconductivity. So what you should know is that the true theory of superconductivity in metals is the Eliashberg theory. And BCS theory is just its weak coupling limit. So in the weak coupling limit, we get the BCS theory from the Eliashberg theory, which is the more fundamental theory. Let's discuss this theory a little bit. So first of all, let me introduce the main parameter in the Migdal-Eliashberg theory and also the main hero of this talk, the dimensionless electron-phonon coupling constant lambda. So phonons induce attractive interaction between electrons, just like photons are responsible for the electromagnetic interaction between charged particles. So this interaction depends on time, retarded, because it takes some time for the phonon to propagate. Therefore, if we Fourier transform it, this interaction U is going to depend on the frequency omega. It's going to depend on omega like this. So this is basically the phonon propagator. It also clearly should depend on the electron-phonon matrix element as G squared. And it also depends on the frequency of lattice oscillators. This is for Holstein model. So for example, if I send the spring constant to infinity, the lattice is perfectly rigid. So there are no lattice vibrations and the interaction must vanish. And indeed you see if I send K to infinity, the interaction vanishes. Now, one thing you might have noticed is that I had K not in the Hamiltonian, but here I wrote K. This is because electrons in turn renormalize the motion of the ions. And in this way, they change the lattice as a spring constant. And this is now the renormalized spring constant here. Now, the electron-phonon coupling constant, lambda, dimensionless, is defined as the value of the interaction at zero frequency, where the interaction is strongest. So we get G squared over omega squared, and also using this expressions for G squared and omega squared, we get mu naught alpha squared over K. Mu naught is the density of states of the electronic states at the Fermi level.
I'm sorry, can I ask you a question in
Sure.
the previous slide?
Okay, yes.
So they hear about the theory that some sense the general theory then the BCS
Oh, yes. Yes.
Theory in the limit of weak coupling. Here the coupling means the electron-phonon coupling.
This lambda, precisely. If you are familiar with the BCS formula for the gap, like omega d by e to minus 1 over lambda, that's precisely this lambda. Lambda. No. This lambda.
This lambda.
Alpha is a coefficient of proportionality in this electron-phonon interaction. Yes.
So in the limit of large lambda, we need to use this Eliashberg theory to describe this superconductivity.
So yes, in the limit, when lambda goes to 0, you get BCS theory. If lambda is equal to 0.1, let's say, the BCS theory is still good, it's very good, but you have some deviations. Now, if lambda is 1, like, for example, for lead or niobium, lambda is for the 1, then the BCS theory is inaccurate.
In what sense?
Like, for example, if you determine TC or the gap from the BCS theory, you will not get the right number.
The real material numbers that.
Yes, yes. But qualitatively, BCS still describes the physics, but the numbers are going to be off.
Sorry, I got confused between alpha and G. I initially thought that G was alpha, but now I saw the formula and I go.
No, alpha is Greek and G is Latin.
No, that I know. Sorry. I thought that the phonon electron interaction was G, but instead is alpha.
Are you referring to the difference between these two formulas?
Sorry. Okay, now I got. Okay.
G squared. G and alpha are basically electron matrix element. They're related through a factor nu naught over n.
Okay.
So
fine.
essentially, one is proportional to the other.
What's the approximation in the Yuzbashyan theory?
In the Yuzbashyan theory, the approximation is that fluctuations around the saddle point, or also in diagrammatic language, vertex corrections are small. So for that, you need the Fermi energy to be much larger than the phonon energy. That's the so-called Migdal theorem.
So the vertex is at the tree level, is computed at the tree level, let's say, while you can do loop corrections, but.
So this we're going a little bit far. It's better to discuss this a little bit later, but in his original work, Migdal computed the vertex on the tree level. But what we can do one loop correction
to the vertex,
to the let's say free energy.
Okay.
And then determine things that way. But that's our work.
Okay.
Original work is just tree level.
Okay.
Okay. So let's derive the Migdal-Yuzbashyan theory. So Migdal and Yuzbashyan, they use a diagrammatic approach to do that. We will use a more modern approach, path integral. So let's write down the Lagrangian that corresponds to the Holstein Hamiltonian. So this is written in imaginary time, the so-called Euclidean action. This is the Lagrangian that goes into the partition function for the Holstein model. So the Lagrangian is quadratic in the phonon field. So the first thing that we do is we integrate out phonons. If we integrate out phonons, that generates electron-electron interaction that I already discussed, quartic terms in fermions. So that we cannot integrate directly. And as usual, to proceed, we decouple these electron-electron interactions with Hubbard-Satonovich transformation. So in this case, you need at the minimum 3 Hubbard-Satonovich fields, these 2 sigmas and phi. I cannot find a good place. If I move here, I'm afraid of screwing up these ports. Okay, so after this decoupling, the action becomes quadratic in fermions again, and now we can integrate out the fermions, the electrons, and obtain effective action that is exclusively in terms of these Hubbard-Satonovich fields. And then we determine the stationary point of the effective action. And as it should be, not surprisingly, the stationary point is the Migdal-Yuzbashyan theory. More specifically, we get 2 stationary point equations, which coincide with Yuzbashyan equations. So these are 2 equations for 2 functions of fermionic frequency sigma and phi. So we get only 2 equations because we assumed time reversal symmetry, and in that case, sigma up and sigma down are equal. So I only have 1 sigma and 1 phi. And in addition, on the stationary point, these fields depend only on the time difference. That's why Fourier transforming I get only one frequency, which is the fermionic frequency, because this comes from fermions, omega n, which is pi t 12 plus 1.
So maybe is related to, again, to the later part of the talk, but the saddle point approximation is good in which, let's say, approximation, or let's say, which.
That's exactly what we just discussed.
Okay, yeah.
Yeah. So what Sergey asked, what Yuzen asks, you can do quadratic fluctuations around the saddle point
Right,
and determine the correction,
correct.
and then see if it's small or not. And then you see that the parameters that govern that correction is lambda, the phonon frequency omega divided by the Fermi energy. So that if the Fermi energy is very large, quadratic fluctuations are small. Okay, and U is this electron-atom interaction that we already discussed. So now we have two independent fields, phi of tau and sigma of tau. I can transform them back to the imaginary time. Let's trade these variables for two new variables, g of tau and f of tau. So I should say that sigma and phi on the stationary point, they correspond to normal and anomalous electronic self-energies. And then G and F, they correspond to normal and anomalous Green's functions integrated over the single particle energy. So if we transform this variable substitution and then compare it to the Eliashberg equations, we derive expressions for Fn and Gn.
Where's your chemical potential?
I don't know, I forgot it. I mean, I didn't bring it today. The chemical potential is it's gone. It's actually gone. It's in Xi originally. Do I have Xi here? Here, you see here, here's the chemical potential. But here, everything was integrated over the single particle energy, and the dependence of the chemical potential disappeared. Okay, so this is what we get for the Fourier transforms of f and g, fn and gn, and by construction, sigma n and therefore gn is real, while phi n and therefore fn are complex. So one thing that you immediately notice from here is that on the stationary point, the field obey the following constraint: gn squared plus mod fn squared is equal to 1. And this is quite important observation. So because it means that we can trade our independent fields for a classical spin of unit length. Indeed, let me define the z component of the spin to be gn and the x and y components to be the real and imaginary parts of fn. Then this constraint means that the length of the spin is equal to 1. And because f and g are my all independent dynamical variables fields, this means that one way or another, I should be able to write the effective action, which is nothing but the free energy functional, in terms of spins. In other words, map the Migdal-Eliashberg theory to a classical spin chain. Indeed, here is the free energy density that we obtain from the path integral by evaluating it at the stationary point. Now, in terms of the classical spins Sn, it becomes the following spin chain Hamiltonian. So more precisely, the free energy is this factor nu naught t times the spin chain Hamiltonian. We separated this nu naught t simply for convenience. So solutions of the Eliashberg equations are the stationary points of the free energy, as they should be. So therefore, they are stationary points of the spin chain, but the stationary point of the spin chain are the spin equilibrium. And the free energy minimum then corresponds to the spin chain ground state.
Could you recall what is N in the original configuration of the free energy density summation index N?
N is a Matsubara frequency. So you see, my things are functions of this Matsubara frequency, like this sigma n. Yeah, so instead of writing sigma of omega n, I write sigma n. It means a function of this fermionic Matsubara frequency. So therefore here, I have sum over two Matsubara frequencies, n and L. And here over one Matsubara frequency, n. And these things are all functions of that frequency.
Sorry, the
No, as it is, then it becomes the index of the spin. And
Yes, and it becomes the position of the spin, n. I'll like spell it out in a second.
sorry, please comments on the meaning of classical spins. What do you mean by the classical? I thought that if S square is much larger than 1, then probably we could say it's classical, but it's equal to
Wait.
1.
I mean, there is a bit of a confusion. So what is classical spin? It's a classical variable that has angular momentum Poisson brackets. It's a vector that has 3 components
Yes.
and fixed lengths. Now the length can be, who said 1 is small? This is like 1 mile. So you can always rescale your classical spin. So this is not the quantum magnitude of spin, yeah,
I see.
which is 1. So if a quantum spin is 1, then actually the spin is h bar times 1, and it's small. But here this is,
It's not.
it's simply a vector. You can forget the word spin. It's a vector of fixed lengths. Okay. It's not a quantum object.
Nice.
So let me describe.
There's a question.
The corrections, so the fluctuations around this, what kind of corrections do you give to the spin Hamilton?
That's an interesting question. It's kind of a little bit unpublished, but they give you, like if here I have only 2 spin interactions, you'll get interactions between more spins.
Okay.
Yeah, like
Here, I think what it looks like is you have a paramagnetic interaction and then sort of a DC field because the sigma z term gives you.
Exactly, yes.
And now you're saying the corrections to take into account, it will give you multi-spin interaction that is still paramagnetic, or you get spin, get sign change.
That I have to say I don't remember the sign, but they are small, in this parameter, in this mid-bell parameter that I described, but I don't remember the sign. Yeah. Okay, so indeed, as you just mentioned, what we have here is ferromagnetic Heisenberg interactions and inhomogeneous Zeeman field. So these 2 things compete with each other. Sides of the chain are the fermionic Matsubara frequencies, again, and the ferromagnetic interaction behaves as 1 over distance squared at large distances.
Why do they compete?
So because at positive omega n, you want the spin to be up.
Because omega can be negative.
Yes, omega goes from minus infinity to plus infinity, and at plus minus infinity, this term always wins, and it enforces the spin to be like that, while the ferromagnetic thing wants them all to be parallel. So let's do a little bit superconductivity in terms of classical spins. I mean, it's fun. So the normal state is a state where the anomalous Green's function f is 0. So this means that spins are going to be simply parallel to the z-axis, up or down. And then to minimize this term, you need spins at positive frequencies to be up and those at negative frequencies to be down. In other words, Sn is the sine of omega n times a unit vector along the z-axis. Now, in the superconducting state, spins acquire X components, tilting away from the Z-axis, and thereby softening this hard domain wall at the origin. So the superconducting transition translates into the spin language as a softening of the domain wall at the origin. So even though the spin representation is just an alternative representation of the Migdal-Eliashberg theory, you could even say a variable change, it changes the way you think about superconductivity significantly, so that a range of properties that were previously unknown, important properties, become easy to see. So,
sorry,
yes,
go back to the previous slide.
sure.
Question. So how do you see that the normal state corresponds to completely polarized configuration?
Because Fn has to be 0. If Fn is 0, you only have the Z component of the spin.
Okay.
So it has to be a up and down.
Okay.
And then you have to determine which up and down configuration minimizes the energy. And the claim is that it is a configuration that minimizes this term, and it is this configuration. So let me give you just one example of a new property. So these are new solutions of the Eliashberg equations. So let's just take the normal state. So we said that the normal state spin configuration is this. So this minimizes the energy in the normal state by aligning each spin along the field that acts onto that spin. But we know that equilibrium can be achieved in two ways, by aligning the spin along the field or against the field. Yeah. So I can take a number of spins here and flip them. So here I flip two spins symmetrically with respect to origin, because the symmetry with respect to origin has to do with particle Hall symmetry, and I want to keep it. Okay, but this is also an equilibrium, right? It's clear that this is equilibrium because fields only have Z components. So all the field from this term and from this term acting on any spin is along Z, and the spin is along Z. So it's an equilibrium. It might not be, it's not the minimum, but it's an equilibrium, which means it's a solution of Eliashberg equations. And as far
Is it like stable equilibrium?
No, it's not stable equilibrium. It's a saddle point. It's a saddle point. Okay. But we think that this kind of solutions, precisely because they are saddle points, play important role in kinetics of superconductors. Because the kinetics will be described by evolution, time evolution of these spins, and these kind of things, they give rise to soliton solutions. Okay, so we, this way discovered new solutions of the Eliashberg equations, but that's not what I'm going to talk about today. So today we want to push lambda, the electron-phonon coupling, to the limit, yet to make it as large as possible. And lambda is a parameter in Migdal-Eliashberg theory, so formally we can consider the limit lambda to infinity. Yeah, the theory might become unphysical or stay physical, but in any case, the formal limit exists. So let's look at this limit. So let's recall the definition of lambda, and then you see that because it's inversely proportional to omega squared and to k, taking lambda to infinity is equivalent to taking the phonon frequency to 0, or equivalently taking the spring constant to 0. If the spring constant goes to 0, it means that ions have no restoring force; they become free. So, this expression for lambda and this expression for U, they were derived for the Holstein model. If I take, the most general electron-phonon Hamiltonian, where phonons have some dispersion and the electron-phonon matrix element depends on the momentum, here is the expression for the electron-electron interaction that I will get. Here too, if I take this as zero frequency, I see that to take this to infinity, I will need to take omega q. At least one way I can do it is to take this omega q's to zero. So in both cases, strong coupling limit is equivalent to vanishing of the phonon frequencies. But if the phonon frequencies vanish, this is what we get. Yeah, this is what we get clearly in the Holstein case, but also in this case, if you remove this, the integral will simply take on the numerator and will call the integrated constant g squared. So in both cases, you just obtain this in the strong coupling limit. So you get the same thing no matter what model you use. It means that the strong coupling limit is universal, independent of microscopic details. The limit is governed just by single energy scale G. For example, Tc is found to be 0.18 times G, and the energy gap is found to be some number times G. So if I measure everything in units of G, these are just dimensionless numbers, irrespective what phonon spectrum I had and what electron-phonon coupling matrix element I had. So therefore, any results we obtain as strong coupling are similarly universal. And by the way, let me also note that the other universal limit of the elaborate theory is the weak coupling limit, which we said was the BCS theory. And that limit is also governed by a single energy scale, which in that case is BCS gap delta naught.
In what sense do you mean here, you use the word universality?
So I simply mean that it's independent of microscopic details, which are the phonon dispersion and the electron-phonon momentum dependence of the electron-phonon couple. And in different materials, we can have different phonon dispersions. In principle, they affect Tc and things like that. But in the strong coupling limit, all models converge to one. So also, while we are at it, let's express G from this equation. Then it's going to be omega times square root of lambda. And let's notice that Tc is unbounded within Migdal-Elaborate theory. If I can take lambda to infinity, I can have a material then with arbitrarily large Tc. So now, since we have the free energy, the easiest thing for us to evaluate is electronic specific heat in the normal state, because in the normal state, the spin configuration is particularly simple. Yeah, so to do so, we just substitute this Sn into this Hamiltonian and then evaluate the specific heat using this formula. And here is what we obtain. Gamma naught T is the specific heat of non-interacting electrons. It corresponds to the first term here. And then we have 1 plus electron-phonon coupling lambda, and this function h of the ratio of the phonon frequency to the temperature. And this function h is given explicitly here in terms of the gamma function. So, various expressions for the specific heat in the Migdal-Elaborate theory were obtained before. But apparently, what didn't occur to anybody is to try to increase this electron-phonon coupling as much as possible. So here are plots for the specific heat, in certain units versus the temperature in units of the electron-phonon frequency omega for 3 values of lambda. And then you see that for this, very large value of lambda, the specific heat is negative in a certain temperature interval. And then it's not difficult to go back to this expression and to analyze it to find that the specific heat becomes negative first at lambda equal to 3.69 in a range of temperatures between T minus and T plus, and moreover, T plus is larger than the TC, superconducting transitional temperature for all lambda greater than 3.69. So this is important because this tells us that the system must be in the normal state, and at the same time, it must have negative specific heat. Okay, so the actual state must be the normal state, but on the other hand, it must have negative specific heat. So these are expressions for Tc and T plus for large lambda, and you see that for large lambda, there is indeed an interval, a large interval of temperatures proportional to square root of lambda above Tc, where the specific heat is negative. But negative specific heat is a contradiction. Yes, please.
Could you please tell us more about this free energy and like formulas from the free energy that you used and specific heat that you used? Because I believe that some derivatives there and
so here is the formula for the free energy.
yeah, but you inserted something.
Yes, it has these variables which determine your state. Then this is free energy for all sorts of states. Now I want to evaluate the free energy for the normal state, in which case I substitute this for Sn and do the calculation. Now it becomes some definite.
So you take the logarithm of the partition function?
You mean what is the free energy?
Yeah, right.
Okay.
Because I'm not really sure that it really applies so well in physics. I don't know which formula I'm using.
The formula is that the partition function is equal to E minus F over T.
Yeah.
It's called free energy. So I mean, this is something you get from the path integral. So let me maybe add that, I mean, what you get is that the partition function is equal to an integral over certain configurations of e to minus this thing. Yeah. So then you say that therefore each configuration has this kind of free energy. But if you want to evaluate it just, at the minimum for a given temperature, then simply, I mean, the whole thing sits like always for a bulk system, it just sits at the minimum of the free energy. So a simple answer, this is just usually defined free energy. Okay, so negative free energy, negative specific heat is a contradiction. It's impossibility because a system with negative specific heat is thermodynamically unstable. So this means that the theory we use to derive the specific heat is wrong. Something is wrong with it. So we conclude that Migdal-Ellsberg theory breaks down for lambda greater than lambda critical, and judging by the specific heat, this lambda critical is about 3.69. By construction, it's still a stationary point, but it's no longer the global minimum. It's some other stationary point. Just one second. So, and because the strong coupling limit is universal, these conclusions are independent of the macroscopic Hamiltonian. Because we did this for whole thing Hamiltonian, we got certain specific heat, but all other models at large lambda will converge to the same answer, and therefore their specific heat at some point also must become negative. So the value of lambda c is not strictly speaking universal. It can vary a bit, but not much. But the fact that there is some critical lambda, finite critical lambda at which the theory breaks down, that's universal. So what this means is that we cannot have a metal with lambda greater than 3.69. Yes, please.
And of course, the corrections for the fluctuation around the saddle, they cannot be extended, but at least so long as the Fermi energy is much larger than.
Yeah. I mean,
but if that fails, we see. I mean, if Fermi energy becomes comparable to the, I mean, if the corrections become important, is there a chance they can fix this, or this is still?
So if Fermi energy becomes comparable to my capital omega, then this theory simply doesn't work. And if you have a metal like that, I cannot say this. So, I mean, here I should add a qualification that metal, like a usual metal. But I mean, in usual metals, it's kind of hard to have a metal where the Fermi energy is, smaller than the phonon frequency. So typically it's orders of magnitude larger. But indeed, that's correct. I mean, assuming that the Fermi energy is large. Okay.
Sorry,
And
this
still the Lashback theory breaks down.
Yes, yes. Even if the Fermi energy is infinite, it
Right.
still breaks down. You know?
sorry, if I understand correctly, this lambda critical for which I mean, you get this negative value for the specific heat.
Yes.
It's not necessarily the lambda for which your minimum is not anymore the global minimum, right?
Yes, very good. Precisely. It's an upper bound on
Correct.
that number.
Yeah.
Yes.
Okay. Yes.
So the theory, but you know, I believe it might be close. Actually, there is an interesting theory by Lyndon Bell. You know, in these gravitating systems, people say there is negative specific heat. Well, actually, there isn't. I mean, if you do things properly, but so there is a conjecture that whenever you have a first order phase transition in canonical ensemble, in microcanonical ensemble, you have negative specific heat. So maybe it's actually the exact mark, or maybe not. But I mean, I don't know.
Okay.
It's speculation. In principle, strictly speaking, it's an upper bound.
Correct. Yeah. Yeah.
Okay, so I mean, we can immediately put this to the test. So we can go and dig up, you know, the most extensive table of lambdas for metals that we have, a reliable one, and see if we find. I mean, when we did this, we actually didn't have idea of values of lambda. I mean, we knew that, like for aluminum, I knew that it was like I think 0.3 something like that, but generally how large it could get, we didn't know. So this is the most extensive, you know, table I found, and the two materials with largest lambda here are, you know, this bismuth and this compound, and the largest lambda is 3.0, you know, which is well beyond this fundamental limit. But I mean, these guys are not highest TC superconductors. So what do you think is the highest TC superconductor?
What do you mean by highest TC super? What do you mean the highest TC?
I mean a superconductor that has the record for critical temperature.
From this one.
No.
What I remember, I mean, I don't remember the material, of course, because I think the record temperature, the one I remember, you have to go to some crazy pressure.
That's very good, very good. So actually, the record is lanthanum hydride.
Yeah.
Okay, so that one, I mean, the latest I saw from 2019 is a critical temperature of 250 Kelvin. Before that was hydrogen sulfide, which was 203. I mean, indeed, these guys are under high pressure, but that's the record. The record is not cuprate, it's not you know, the experiment-based superconductors, but these guys are the record.
So the reason why you believe that this is a tight upper bound is based on this, or
No, wait, just I'll comment on that. But first, let me finish the thought. So now, you know, we went and actually, I mean, this was provided to us by an experimentalist. So this is the largest value of lambda we could find. And you see that, you know, at this pressure, it's, you know, pretty close to saturating this bound. But I should say that, you know, this has to be taken with a grain of salt, because unlike this, these are not that well verified values. I mean, they seem to be like, okay, but these are just ab initio calculations, not results that you get from experiment. But the reason I believe this might be, how do they say it in mathematics?
tight.
No, but okay, let's use tight. Tight upper bound is, you know, that maybe indeed, until the specific heat is positive, the theory is still okay. Like that specific heat is an indicator of that.
So wait a second. So these are experimental data?
No, these are ab initio calculations. these are taken from experimental data. I mean, not directly. That kind of, you measure the spectrum of phonons, and from there you can evaluate lambda.
No, my question is the TCs.
No. This TCs, I mean, the ones that I mentioned before when I said a record, that's really measured.
Right.
So in lanthanum hydride, there is a paper, different paper in Nature, not this one, from 2019, that says that they measured 250.
That's an experimental result.
That's experimental result.
Okay. So what is then non-experimental here? The estimate for lambda or what?
This specific table was done by people who do ab initio calculations.
How does that relate then
To the record?
to the experimental data?
No, so the only relationship is that what I'm saying is that if we want to find largest values of lambda, we better go to this material because they are known to have largest TC. And then this 3.62, might be the largest, value of lambda that we know. Yes.
Do you expect to observe in experiment kind of the tendency that the decreasing the specific heat as you increase the lambda?
Yeah, absolutely. I think it's even has been observed. Yes. Yeah, I mean this if I go these curves, I mean they work, but you should keep in mind that this is only in a certain temperature interval. Like in other temperature intervals, they grow. But I think these curves work in experiment. I mean, of course, 4.5 does not exist, but I mean for like smaller lambda. Also, a bound on lambda implies an upper bound on TC. So we can use, because this lambda is pretty large, we can use this large lambda asymptote from the Migdal group theory, and then we get the TC in unit of omega is 0.35. Maximum. It should be less than that. And indeed, then we see that these two materials are close to the upper bound. Okay, so now I will move to trying to make sense of that and to trying to understand what happens with the system. So the fact that the specific heat becomes negative, and it's a specific heat of electronic quasiparticles. It means something is very wrong with electronic quasiparticles in our system. And we can try to see that by looking at the quasiparticle lifetime. So we know the normal state Green's function, is generally known, and also it follows from the path integral. And now recall that sigma, was related to G like this, and G in frequency domain is the Z component of our spin and is equal to sine of omega n in the normal state. So then Fourier transforming this relationship and substituting this for Gn, we obtain this expression for the normal self-energy sigma n. And now, in the strong coupling limit, as we said, this omega goes to 0. It means that n equals to m term diverges. So let's keep just that n equals to m term because it dominates. Then taking this n equals to m term, this cancels, and then I get g squared over omega squared, which is lambda. So I get this answer, lambda pt sine omega n. So now I can analytically continue that and obtain the retarded Green's function. And the imaginary part of the pole at psi p is the quasiparticle decay rate gamma, which is inverse quasiparticle lifetime. So we get lambda pt for that, which is much greater than temperature, which means that for large lambda, it's much greater than temperature, which means that the quasiparticles are not well defined. And moreover, when lambda goes to infinity, the lifetime vanishes, means that fermionic quasiparticles are very sick. So they are not good at all in that limit. Okay. So let's look, I mean, this must be happening because of the electron-phonon interaction. So let's look at the electron-phonon interaction. Now, again, at strong coupling, omega is small, and therefore the temperature is going to be much larger than omega. And if the temperature is much larger than the oscillator frequency, it means that the oscillator is classical. It has very large quantum number, and therefore it's classical. We can treat this xi approximately as a classical variable. But if we think about this xi as a classical variable, then this whole thing we can interpret as on-site potential Vi, on-site random potential. It's random due to temperature fluctuations. So then, keeping only the classical phonons, this is a problem of electrons moving in a random impurity potential. And there is a known formula for the decay rate due to non-magnetic impurities. So in our case, this average of Vi squared is going to be proportional to average of Xi squared, which we will simply evaluate by using an equipartition theorem for harmonic oscillator, and then recalling the definition of lambda, we get that this decay rate due to impurities is lambda pt, which is exactly what we also got from Migdal-Edwards theory by keeping the divergent term only. So therefore, this effect of vanishing of the particle lifetime is due to classical phonons. And classical phonons are just thermal fluctuations of the static displacement of lattice ions.
And why would they make the lifetime then?
Because it's a lifetime of kind of wrong quasiparticles. Yeah, like there are some real quasiparticles which are okay, but these quasiparticles are plane waves, like delocalized electrons. But when you create a very large potential, these are no longer the true eigenstates. So that's what, and the stronger the potential, the more, I mean, we see that effect.
Another question, the XIs are still time dependent. Even if we keep them classical, they are still time dependent because these are oscillators. So where's this time dependence gone?
Yeah, so I'll talk about it a bit more, but so we have to think about this in a partition function. So in a partition function, we average over different configurations. That is over different, so we replace basically the time dynamics, that's just the nature of the partition function, with like sampling over, with average over the phase space.
Yeah, but I mean, what you before tried to say is that your electrons now see some kind of disorder potential, so therefore the plot states are not anymore good. Is not a good basis, so to say, right? But on the other side, the oscillators are still oscillating. So on some time scale, I will just again recover a translation variance, so to say. Because the average of X is so to say going to vanish. So where's the catch here?
So
I had a question because I had a very similar
Sure, okay,
question.
yeah,
Because,
yeah.
Well, correct me, because I was also thinking why can you treat it as a random potential? Basically, to me, only implies that the time scale on which this random potential changes should be much longer than the dynamics of the quasiparticle. Because only then you can assume that the potential is static to the average. Is how I
So guys, but I mean, what we have here is a partition function. Yeah. So suppose like you want to evaluate the partition function for an oscillator. I mean, just single oscillator. So you can do that, right? And you don't ever have to make momentum or the coordinate time dependent. So it's a similar thing here. If it's a quantum, you cannot do that because you have dependent on imaginary time. But when you don't have simply momentum and the coordinate separate, and you are just averaging over different realization of oscillator positions. Now, on average, it's translationally invariant, but there are these fluctuations. even though average of xi is 0, average of x squared is not 0, and that is what is causing this decay. Okay, so actually that's what I'm going to talk about next. So let's now say that all our oscillators are completely classical. That is dramatic simplification, but let's just say that for a moment. So then in Holstein Hamiltonian, I put bar here indicating that they are classical variables. So then imagine putting this into partition function e to minus ht and integrating over this classical momenta and coordinates. Then momenta are independent variables and they just integrate out. And what you are left is precisely with electrons moving in a certain on-site potential xi, but this potential comes at certain elastic energy cost. But on the other hand, we know that in the strong coupling limit, k goes to 0, ions become free, and this potential energy cost disappears. And if that happens, then if you erase this term, it's clear that, and you have this potential in your hands, that it will always be energetically favorable if alpha is very large to generate a non-uniform potential for electrons and to lower the energy that way. In other words, this xi must acquire non-zero averages, breaking lattice translational symmetry and giving rise to charge density wave order. So that's what we expect to happen here.
Could I ask a question? Is it important that this potential changes with time, normally with time of oscillations of phonons, or these times are too large with respect to electronic times?
This potential doesn't change with time.
But still, the phonons are vibrations, so this I agree that this is random potential, but as far as the atoms are oscillating, it should be somehow this potential should change in time.
No, I mean they are not oscillating. So what is statistical mechanics and what is partition function? So like in reality, you have a system, it moves, it has certain trajectories, it moves, yes? But we say that we can replace averaging over time, let's say you want, with averaging over phase space. And as soon as you turn to the average over phase space, you don't have time dependence. It's just you're averaging over different realization.
That's true, but you just said it. It's still equivalent to a time, an average over time. So I guess Sergey is asking, well, what happens if I take that viewpoint, and how is this still time-dependent oscillation of my classical phonons going to affect or not to affect? I think that's what.
Yeah, you can. I mean, take that view as well. I think if you go to times that are much larger than your oscillation times, this refers to that. So like we go to, those times. We look at the quantities at times that are much larger than this kind of relaxation time. Okay, so right. So to illustrate this, let's look at this at a simple case. So let's consider a square lattice at half filling, and let's consider this lattice distortion pattern where each lattice ion is displaced by amount delta x in the direction opposite to its nearest neighbor. So now when we specified xi, it is straightforward to substitute this into the Hamiltonian. It is quadratic in fermions, and we can determine the spectrum. The spectrum features a gap in the Fermi energy, the so-called Pauli's gap, which is alpha delta x. Okay, and then you can see that the solution with non-zero delta x always has lower energy, breaking the translational symmetry of the original lattice. So what we have here is a a metal-insulator transition, because that's what gap opening at the Fermi energy is. So though this is at half filling, at lower fillings, we believe we can also get Fermi liquid to Fermi liquid transition, but still accompanied by lattice translational symmetry breaking. So let's try to understand, where this trouble with classical phonons arises in the Migdal-Eliade theory. So now classical variables are independent of imaginary time. So the dependence of imaginary time only arises when you have things non-commuting. So therefore, they sit at zero Matsubara frequency. So if this xi is a classical variable, it's independent of tau. I do transform to frequencies, then its frequency image is going to be only have one non-zero frequency component when the frequency is equal to 0. So now let's take the phonon field. We can separate it into the classical part, which is a zero frequency part, plus a part that contains all other frequencies. This part is a quantum fluctuation of this field. And now let's look again at Holstein-Lagrangian. So notice that this part here is independent of tau, so it does not contribute to this term. Now, in the strong coupling limit, k goes to 0, so this term goes away. And then we see that the Lagrangian is going to be linear in this xi bar. But if it's linear, it's illegal to integrate out this field, because we can only do Gaussian integrals, but now the action is non-Gaussian. So that apparently where the trouble comes from integrating out this classical part. So instead, we can do, it's more natural and correct to include this zero frequency part into the single particle part, into this single particle part by replacing the Hoping with the Hoping plus alpha xi. So then these classical phonons, they become a variable potential for fermions. And this variable potential is itself subject to minimization. So now we have fermions in an adjustable potential interacting via quantum phonon exchange, because with the rest, we'll do just like what we did in the Migdal-Eliade theory. They will lead to an effective electron-electron interaction. So then we will have the same path integral derivation as before, but now for arbitrary potential VI, which is also subject to minimization. So the theory that results from this, we called lattice fermionic theory of superfluidity, and I'll say a few words about it later. But before I do that, let me, not to give you a too simplified picture that, everything is classical phonons, let me say that the specific heat, the negative specific heat, is actually due to purely quantum phonons. Moreover, the contribution of the classical phonons cancels from the free energy altogether, because the phonon frequency here is this transfer frequency omega n minus omega m, this omega p. So classical phonons, they contribute, they are n equal m term, but the n equal m term cancels here, because when m is equal to m, this I get Sn squared here, which is 1 minus 1, 0. So this term simply identically cancels from the free energy. Therefore, the entire free energy and specific heat are due to quantum phonons. In fact, the negative specific heat is a consequence of having this hard jump at the origin. So let's do a little calculation quickly of the specific heat coming from the interacting part of the free energy. So if two spins are at positive frequencies, then this dot product is 1, so this goes away, cancels again. When they are at the negative, again, so only spins across the origin contribute to the interacting part of the free energy. So now, in the strong coupling limit, omega is 0, so this is simply proportional to 1 over omega p squared. And there are p ways to have spins at distance omega p from each other across the origin. So then we'll get this expression. Now converting this to an integral, the smallest distance between spins is 2 pi t, so that's our lower limit of integration. And the upper limit will cut off the integration at some lambda, and we'll get this logarithm. When differentiating lambda, dependence on lambda will disappear, and we'll get precisely this formula. So this is simpler than before because we are working in the strong coupling limit. Okay, and indeed we see that the specific heat is negative when T is smaller than T plus, and this is what we get for T plus, and it's larger than Tc, so the story that I already told you. So, but now, suppose a gap opens either of superconducting or insulating origin in the quadriparticle spectrum. So now the equation for Z component of spin changes like this. So notice that if this gap, let's say this Piles gap delta P is 0, I will get omega n plus sigma n divided by mod omega n plus sigma n. That will give me just the sign of omega n because this is an odd function. Okay, but now with this change at small omega n, sigma n is proportional to omega n at small omega n. So this goes to 0, but the denominator goes to a constant. So the Z component of spin goes to 0 at small frequencies. So therefore, spins at frequencies of order delta p do not contribute to the free energy, which means that now we have to cut off this integration at delta p rather than at 2 pi t, and then we get a constant and we get a positive specific heat. So I'm just showing you that this negative specific heat comes from this hard jump, and that gap opening cures that. So what I'm trying to say that even though classical phonons don't contribute to the specific heat directly, they stabilize the system by opening a gap at the Fermi level, because this gap strongly modifies the contribution of the quantum phonon to the free energy and forces the specific heat to change sign from negative to positive. Okay, so I already talked quite a bit, so let me tell you what this all means in terms of phases and phase transitions to have a certain picture. So let's look at the profile, a schematic profile of the free energy. So suppose we are below the critical value of lambda, which I rounded to 3.7 here. So then we have the usual metal superconducting transition, and the usual Migdal error theory works. So at high temperatures above the superconducting transition temperature system is a normal state. Then through a second order phase transition, the superconducting state becomes the new minimum and the normal state becomes the saddle point. And so the system now is in the superconducting state. Now here is the implication of what we found, that at lambda greater than the critical value, the situation is as follows. At very high temperature, we just inevitably have to be in the normal state. We just have a normal gas of electrons and phonons. So we are at a normal state, and the specific heat is positive. Now, at this temperature T plus, we found that the specific heat became negative. So at that temperature or around that temperature, a new minimum developed, which for definiteness I take to be the insulating minimum here. So it develops, and as the temperature lowers, it becomes deeper and deeper. So by the time that the superconducting minimum appears, because solutions of the Eliashberg equations still exist, but they no longer describe a minimum, the superconducting, no, I shouldn't say minimum, superconducting stationary point must appear again close to the normal state at some point. But because this has already developed quite a bit, it's going to be much lower than the superconducting minimum. So at least for some time below, for some temperature range below Tc, the system still remains in this insulating minimum. And what this also means is that I have a first order superconductor insulator phase transition as a function of lambda at fixed temperature. So suppose I fix the temperature at this point, and then at lambda greater than 3.7, I am in this insulating minimum. But now let's change the lambda to be smaller than 3.7. Then this minimum disappears, and I have to be in this minimum. Okay, so it's a first order phase transition between the two. Okay, so any questions? And also, how am I doing on time?
Well, you exhausted quite a bit of that, so
Okay.
I would say, how long do you need?
I think it's I think like maybe 5 to 10 minutes.
5? That would be fine.
Okay, so I'll do things quickly. So the question is that after the Migdal theory breaks down, we no longer have a quantum description of the system. So can we develop a new theory that remains valid and strong coupling and describes a new state? I kind of already hinted on that. I call this lattice fermionic theory that results from including the classical phonons into single particle part. And here is what you get in this case. So it's interesting. It's more complex than the Migdal-Elaborate equations, but it's still doable in polynomial time on a computer. So now we don't assume translational invariance. So what you have here is a nonlinear Schrödinger equation. It's nonlinear because we minimize with respect to a single particle potential, and then the single particle potential depends itself on the electronic states. Okay, so you have to solve this equation to get the single electron state, this pi I gamma and energies epsilon gamma. But this is coupled to these three Eliashberg-like equations, where U and M is the electron-electron interaction as before, but they are coupled because this N gamma here, it depends on this field itself. And this theory, it reduces to Migdal-Elaborate theory in translation invariant case, and also it reproduces some other theories in other limits that people constructed. And also, just one last thing, if you type into Google breakdown of Migdal-Elaborate theory, you will find maybe 10 or more papers that talk about that. But I want to say that that is actually, like what we discussed today was a real breakdown, and that is a fake breakdown. Okay, so in what sense it's fake? So we already said that electrons are normalized phonon frequencies. So you can find exactly how they renormalized it. So this was done by Migdal and Eliashberg originally, and then it's also written in this textbook. So now with that, I can define, which I didn't do, but I can define a bare electron-phonon coupling as a ratio of G squared to the bare phonon frequency. And mine, the one that I defined before, was renormalized electron coupling. And then you can see that renormalized coupling, scales this way with bare coupling, okay? And then you notice that when lambda naught goes to 0.5, phonon frequencies become imaginary, so the lattice becomes unstable. So for this reason, Migdal and Eliashberg restricted their theory to lambda naught less than 0.5. Okay. So nowadays, people rediscover this and say that this is a breakdown. But is it really a breakdown? And also notice, by the way, that even if this was a breakdown, it doesn't give any upper bound on lambda, because as lambda naught goes to 0.5, lambda goes to infinity. But moreover, actually, this lattice instability is fake. It's precisely an artifact of the effective Hamiltonian description to which I alluded before. So if you use this Hamiltonian, the fundamental, there is no such instability. So, this was discovered by Roman and Kagan originally. So let me just, read this and finish with that in the use of Hamiltonian of the Frolic type, an illusion arises about the strong renormalization of the phonons, which also leads to instability of the lattice in some cases. Well, actually, this does not occur because in the effective Hamiltonian, the phonon should be already renormalized. It's already effective Hamiltonian itself is a result of renormalization, and secondary renormalization is going to be double count. Okay, and what people agreed since then to do is not to renormalize phonons. Yes, thank you for your attention.
Emil, for this fantastic talk. We still have time for some questions. Yes. That's your
Simple generalization. So how does electron interaction, where in electron interaction will appear is lemma?
Yes, that's a very good question. So there is a way to include Coulomb interaction between electrons into this theory. I mean, this, like in the usual treatment, this gives rise to the parameter mu star. So the way it will affect it, that it will make lambda lower. I wanted to create most, because obviously this repulsion, it competes like it's an enemy of superconductivity. I wanted to get lambda as large as possible. That's why I eliminated that, yeah?
So the question is like, it will always lower the possibility of having higher DC, or it can also go the other way?
The electron interaction?
Yeah.
No, it decreases TC, it suppresses TC. So it's not our friend. Like if you want to get lambda to be as large as possible, or TC to be as large as possible, you want to have that as small as possible.
More questions? What about the famous anomalicity of phonons? What if you do the same, but on the phonon side, you add some kind of anomaly terms?
Mm-hmm. I haven't thought about it, so I'm not sure. I mean, but we can think about it. It's an interesting question. So I don't think it will, I doubt it will change the fundamental fact that the theory breaks down, because it's independent in that limit becomes independent of all this kind of details. Basically, the interaction is so strong that it dominates everything. But it's interesting to see if anharmonicity can lead to some interesting effects. It can modify the critical value of lambda for sure. Maybe that is a way to increase it.
Okay.
I don't know.
We have a question from the Zoom. Aniket Patra, please unmute yourself and go ahead.
Hi, Emil. So when you map your free energy to the spin Hamiltonian, then you mentioned about the Poisson bracket relation for the spins. So I was wondering, what does that mean in terms of the original Eli-Eshberg theory?
Well, in terms of to see that, yeah, you need I think dynamics. Yeah, right. Because they appear in the Hamilton equations of motion. So I think what it means, it's just you get, for these averages that are introduced, in principle, you can write some equations of motion, like kind of Heisenberg equations of motion. Mm-hmm. And then if you do all the averaging, etc., this will become classical equations of motion for these spins with this Poisson bracket.
Ah, I see. And also another question was that when you were calculating the specific heat for the normal state, then did you only calculate it for this normal state where you have all spins up for energy or frequencies above zero and all spins down for frequencies below zero, or did you include those type of excitations that you said that can contribute to soliton solutions?
No, this was done for the the minimum. Yes, so for this configuration that minimizes the free energy. Because if I do it for other solution, that's not going to have a meaning of the specific heat you get in equilibrium. That's going to be something else.
Ah, okay. Thanks.
Sure.
Okay, more questions? If not, then I think it's time to finish and move to food. Thank you very much, Emil, again, for your.